Hello and welcome to this midterm demo on Demonstrator 1 called Smart Connected Factories of the Future. In this demo, I will show you scenario 1 as described in deliverable 5.1 related to that of predictive maintenance. There are multiple components that have been used in this demonstration. Each component then belongs to a specific architecture block as defined in the elastic architecture, and then each component, depending on its function, addresses different key roles. In order to explain this better, I'll use a demo sequence to walk you through the demo flow. It starts with a DevOps engineer setting up the relevant infrastructure and the CI/CD pipelines where all the processing and application components are then deployed. We have a data scientist and a data integration specialist who are developing data-driven applications. They write their code using eBPF technologies or WebAssembly. And when they write this eBPF code, we have integrated this into the CI/CD pipeline and have used the static eBPF analyzer code that can highlight any vulnerabilities. So once the code is written and then passes the CI/CD system, it is then deployed. Then the security specialist wants to configure different trust policies related to data production or data consumption or data handling. So the security specialist configures various trust policies and enables then secure data handling. And in order to enable secure data handling, the idea is that the security specialist can explain which components need to be verified before they have to be deployed. After that, the system is ready to start collecting data, being able to do data processing, and then also data can then be consumed. And these different WebAssembly components are then deployed using the propeller orchestrator written by abstract machines. So now you have data being collected, processed, consumed, etc. And then you want to monitor how the system is doing. And then we have a bunch of frameworks that are used for that. The first one is the eBPF observability framework, which allows monitoring for any errors that occur within the system. The second is related to AI intrusion detection, where any malicious traffic flows can be detected. And the third is then Netto, which is used to analyze how much CPU is being used by the kernel during these traffic flows scenarios. So with that introduction, let's take a quick look at the demo. The first thing is then the prerequisites and setup, where you can see we have in-network computation infrastructure, we have some general purpose hardware, and then we have VMs with TEEs available. So this is already set up. In addition to that, for the purpose of this demo, we'll be using the WebAssembly applications that have been written for the demonstrator. This WebAssembly application then performs filtering and aggregation of data. And then we also have code for doing some additional filtering using CBOR. So these are all already deployed in the relevant infrastructure. And as I had mentioned, for eBPF and XDP code, we are using the the eBPF static analyzer to analyze the vulnerabilities or any issues with the C code. And that we have integrated with our CI/CD pipeline. So for example, in this particular case, there is an error, and that error can be visualized by the pretty verifier. So it basically points out where there is a potential error and what fixes should be made in order to rectify the issue. Okay, so now that we have our infrastructure in place and we have written our code, and then that code has passed through the CI/CD machinery and it has now been deployed into the system. So then comes the security specialist, and what the security specialist wants to do is configure trust policies. These trust policies are basically bound to the different types of data that is required, and in order to be able to describe the data, we have something called data models. These data models are described in a format called a semantic description format, which we are now standardizing at the IETF. For the purpose of this demo, I'll use the elastic motor object. The elastic motor object is a simple object which basically indicates that the motors then send three pieces of information: the rotations per minute, the vibration information from the sensors, and then the temperature of the sensor. So these are the three pieces of data. So then back as the security specialist, what I want to do is configure a trust policy. There can be different policies for production. For example, if you want to validate provenance and lineage information, or if you have sensitive data and you want to validate that the consumer is able to then process this data securely, then you have data access and consumption policies. And then if you want to ensure that also the data is being processed within the network in a secure manner, then you have data processing capabilities. For the purpose of this demo, I'll use the data access and consumption policy, and then I will associate it with the elastic motor object. Okay, so then we have configured the trust policy. The next thing then to do is to start the data transfer. For the purpose of this demonstration, I have already started a simulator that is producing data. So it sends 5 seconds of normal data, and then for 5 seconds, it simulates some kind of error scenario, and it keeps doing that in a loop. So what I want to now do is then initiate a data consumer. So I'll create a new data consumer. Let's call this data consumer 1. I want to use the HTTP protocol, and then I want to also say that I want to receive all these three pieces of information. We could enable data handling, but I will come back to this again in just a moment. So let me go ahead and create this consumer. So first of all, the system detects that a trust policy was configured, and so it basically gathers the evidence from the consumer and then sets up the requested access channels. So then there is a binding between the freshness of the request and then the identity of the consumer, and based on that we get back a URL with which that data can be accessed. So let's copy this URL and start consuming the data. In order to visualize what is happening, I have a little visualization tool which depicts a motor. And what you see on the right side is the data that is being generated. So as mentioned, for 5 seconds, it's sending good data, and 5 seconds, it's sending bad data. What you notice here is that all the data is then being received by the consumer, whether it is in a good condition or whether it is in a faulty condition. And often this is not really desired. You only want to know when things are actually not working correctly. So that's where the orchestration capabilities and the WebAssembly capabilities developed in Elastic come into use. So let's go ahead and create a new consumer. Let's call it demo consumer 2. Let's make sure that we consume all the same data, but this time let's enable the SendML filtering and aggregation. And for this filtering, we need to provide it some configuration. And so we say when the value or when the object is equal to that of vibration and the value is greater than or equal to 1.0, only then send me those particular values. So again, the trust policy is detected, and then the evidence is being collected, verified, and the access channels are then being appropriately set up. Okay, so then let's copy this new URL and let's reinitiate data consumption. And then when we go back to our motor visualization, what we see is that in the period of good data, no data is actually being received because it is being filtered out within the network. And then only when there are potential errors, those errors are then displayed. And you will notice that that happens only when the vibration value is greater than 1.0. So this demonstrates the orchestration capability as well as the WebAssembly capabilities that we have used in the system. Lastly, to show you the observability capabilities developed in Elastic, the first one I'd like to show you is the eBPF-based monitoring capability. So for example, when there are errors in the attestation process, so first of all, the attestation process involves validating the different types of data that has been requested. gathering the evidence from the orchestrator, submitting evidence to the verifier, and once all of this is completed, enabling the data collection, and then generating any data access token, returning it to the consumer. So in this particular case, what you notice is that step 3 has failed, where the evidence to the verifier was submitted, but then you see the error that the verification of the attestation evidence actually failed. This has then been developed using the SpinCube framework. We have decomposed our application into a serverless style application, and then the framework that has been developed in Elastic automatically allows us to view these sort of errors that occur within the system. No extra code is really needed. However, in order to be able to describe these in the form of service flows, we have to inject different headers so that we get this OpenTelemetry style logging capability. So that's the first observability tool. The second observability tool is that related to any intrusion detection capabilities. So in this particular case, several different malicious activities have been detected. And in order to analyze that, basically the AI intrusion detection system is sending alerts to the data fabric system. And here, for example, it indicates from the source IP address, the destination IP address, and provides an error message saying what is the potential issue. Last but not least, we also have the observability tool for monitoring how the system is behaving in terms of its performance. So here we have the Netto tool, which is measuring the CPU time consumed by the kernel for these data flows. And then it has these different classifications to further enable granular understanding of where the CPU is being consumed in case of any bottlenecks. So that concludes the demo that we have built for the MVP, and thank you for your attention.